Imagine holding a glass of water in your hand. You can see it, feel it, even taste it. But what if I told you that everything you're experiencing, every drop, every sensation, is built from things you can never see, touch, or taste directly? For centuries, the idea that matter is made of tiny, indivisible particles called atoms was just that, an idea, a philosophical guess. Today, we talk about atoms as if their existence is obvious, as if we've seen them with our own eyes, but have we? Why do we actually believe atoms exist? What is the real evidence, and how did we come to trust in something so small, so invisible, that it defies our senses? Let's start at the beginning. The concept of atoms goes back over 2,000 years to ancient Greece. Philosophers like Democritus imagined that if you kept cutting matter into smaller and smaller pieces, you'd eventually reach a point where you couldn't cut any further. These ultimate building blocks he called atomos, meaning uncuttable. But this was just speculation. There was no experiment, no microscope, no way to test the idea. For centuries, the atom was a philosophical curiosity, not a scientific fact. Fast forward to the 19th century. Chemistry was booming. Scientists were discovering that elements combined in fixed ratios to form compounds. Water, for example, always contained 2 parts hydrogen to 1 part oxygen. This was a clue. Maybe matter really was made of tiny, countable units. John Dalton, an English chemist, revived the atomic theory, arguing that each element was made of its own kind of atom, and that chemical reactions were just rearrangements of these atoms. But even Dalton couldn't see atoms. His evidence was indirect, based on the patterns he saw in chemical reactions. So why do we believe in atoms today? The answer is a story of evidence, layer upon layer, each more convincing than the last. It's a story of clever experiments, bold ideas, and the relentless pursuit of truth. One of the first big breakthroughs came from the study of gases. In the 1800s, scientists like James Clerk Maxwell and Ludwig Boltzmann developed the kinetic theory of gases. They imagined gases as huge numbers of tiny particles bouncing around, colliding, and transferring energy. This theory explained why gases exert pressure, why they expand when heated, and why they dissolve into each other. The math worked beautifully, but still, no one had seen an atom. Then came a crucial experiment, Brownian motion. In 1827, the botanist Robert Brown observed that tiny pollen grains suspended in water danced around in a jittery, random way. At first, people thought this was just life or some mysterious force. But decades later, Albert Einstein took a closer look. In 1905, he showed that the random motion of the pollen grains could be explained by collisions with invisible water molecules, atoms in motion. Jean Perrin, a French physicist, later confirmed Einstein's predictions by carefully measuring the movement of tiny particles. For the first time, scientists could calculate the size and number of atoms in a drop of water. The evidence was piling up, but the story doesn't end there. In the late 19th and early 20th centuries, new experiments began to reveal the structure of the atom itself. J.J. Thomson discovered the electron, a tiny, negatively charged particle inside the atom. Ernest Rutherford's famous gold foil experiment showed that atoms are mostly empty space, with a dense, positively charged nucleus at the center. Niels Bohr and others developed quantum models to explain how electrons orbit the nucleus. Each discovery added detail to the atomic picture, but also raised new questions. What about direct evidence? Can we actually see atoms? The answer, surprisingly, is yes, at least in a sense. In the 20th century, scientists developed tools like the scanning tunneling microscope, STM, and atomic force microscope, AFM, which can feel the surface of materials at the atomic level. These instruments produce images that show individual atoms arranged in patterns, like bumps on a surface. We can even manipulate single atoms, moving them one by one to spell out words or build tiny structures. These images are not photographs in the traditional sense, but they are as close as we've ever come to seeing atoms. But perhaps the most convincing evidence comes from the way atoms behave. Every time you turn on a light, you're seeing the result of electrons jumping between energy levels in atoms, releasing photons of specific colors. The entire field of spectroscopy, studying the light emitted or absorbed by substances, depends on the atomic structure. The patterns of lines in a spectrum are like fingerprints, unique to each element. and they match perfectly with the predictions of atomic theory. Nuclear reactions provide even more dramatic proof. When atoms split or fuse, they release enormous amounts of energy, as predicted by Einstein's famous equation E equals mc2. The existence of isotopes, atoms of the same element with different numbers of neutrons, explains why some materials are radioactive and why nuclear power and nuclear weapons work. The periodic table itself, with its repeating patterns and predictable properties, is a triumph of atomic theory. So why do we actually believe atoms exist? Because every experiment, every observation, every technological advance points to the same conclusion. The evidence is overwhelming, from the behavior of gases to the colors of stars, from the structure of crystals to the power of the sun. Atoms are not just a convenient idea. They are the foundation of everything we know about matter. But there's a deeper lesson here, one that Feynman loved to emphasize. Science is not about absolute certainty. It's about building the best possible explanation for the evidence we have. The atomic theory is not a belief. It's a model, a way of understanding the world that has passed every test we've thrown at it. If new evidence came along that contradicted the existence of atoms, scientists would have to reconsider. But after more than a century of experiments, the atomic model stands stronger than ever. Feynman once said, if in some cataclysm all of scientific knowledge were to be destroyed and only one sentence passed on to the next generation of creatures, what statement would contain the most information in the fewest words? I believe it is the atomic hypothesis that all things are made of atoms. Little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. This simple idea unlocks the secrets of chemistry, biology, physics, and even the universe itself. So the next time you look at your hand, a glass of water, or the stars in the sky, remember, you are seeing the evidence of atoms everywhere. You are made of atoms. Your thoughts are the dance of atoms. Your life is the story of atoms coming together and coming apart. We believe in atoms not because we want to, but because the universe insists on it in every experiment, every observation, every moment of existence. And that perhaps is the most beautiful thing of all. The invisible world of atoms is not just a theory. It's the reality that underlies everything we see, touch, and know. It's the bridge between the seen and the unseen, the known and the unknown, the world of experience and the world of explanation. In believing in atoms, we are believing in the power of evidence, the triumph of curiosity, and the endless adventure of discovery.